All right. So again, what you see before you is a list of problems that I've done either after class, in office hours. So you might want to do a screenshot of this or refer to the video on this later on. Okay, I will post the video with this. All right. So yes, all the homework. Okay, so I'll get to that in a moment. Yeah, everything's due December 14th. Okay, so again, this is going to be in the video. All right, the list of homework questions that I've done by now. I'm sure we'll do more at the end of today's class, and also a lot on Thursday. You're going to want to tune in or get that Thursday video, right? Where we'll do a lot of questions, I'm sure. All right. So here is the plan. We've stuck to the plan basically. All right. So I'm going to finish up chapter 10. I have a bunch of goodies today. All right. I'll tell you what's optional and what's really required for the homework. We'll have some time for questions at the end, but we have a whole lot of time for questions on Thursday. So today, I've time to discuss chapter 10 in detail, have some goodies. So we'll probably end around 9:15 or so today. I'll take questions at the end, and we'll have the whole session on Thursday to address questions. So we'll have a lot of time on Thursday. The Alex and the homework for all of this stuff, chapters 7 through 10. Okay, all this homework will be due on Monday, December 14th. And remember, it is a 250 point assignment. It's worth a lot. Okay, any other comments I need to make about that? Let's see. All right, 250 points covering all this. And I do hope to finish the chapter 4 homework by, I'm saying, the end of the week, this weekend as well. And then the 5, 6, and the final, the 5, 6, and the 7, 10. I'll be doing a lot of grading around here. All right. So I should be wrapped up by Christmas time, I'm hoping, by the 25th, I'm hoping. But these are rough estimates. Okay, we'll see how it goes. All right, any general questions? So yeah, everything's due at, well, no, yeah. Okay, at the end of Monday, December 14th, right? End of Monday, December 14th. Okay. Any general questions about the schedule? Any general questions about the schedule? All right, we're recording. So let's begin. Okay. Let me move this over here. All right. So in fact, this first part will be optional. I'm going to explain why a formula works with ellipses. So in this playlist, we'll keep an eye on what's optional. And at all times, well, let me show you this. At all times, of course, check for corrections and notes over here. Right. Okay. So let's start with an optional video about why a certain ellipse formula works.
Everyone, I'd like to explain why this formula works for ellipses. C squared equals A squared minus B squared. There's no plus sign here like for the Pythagorean theorem. We are using the Pythagorean theorem, but in a different way. Now, what's the cast of characters again? Who are A, B, and C? So here's a horizontal ellipse, for example. A, the semi-major axis, is the distance between the center and either vertex. B, the semi-minor axis, is the distance between the center and either endpoint of the minor axis. C is the distance between the center and either focus. Again, what's the relationship between A, B, and C? C squared equals A squared minus B squared. That's how we can find C eventually. A and B we can get pretty directly from the standard form for the equation of an ellipse, whether it's centered at the origin or translated. But how do we find C? We find it through this formula. C squared equals A squared minus B squared. Now, what are some principles that will help explain why this is true? Remember how we can construct an ellipse. We can tie down the endpoints of a string at the two foci of the ellipse, draw the string taut by a marker, and then rotate the marker, keeping that string taut, and create our ellipse. A key question is, how long is that string? Well, remember, one of the properties of an ellipse is that let's say you take point P1 and you take the sum of the distances between this point and the two foci, d sub 1 plus d sub 2. It's a property of an ellipse that the sum of those distances equals the sum of the distances d3 and d4. For this point, p sub 2. P sub 2 is another point on the ellipse. The sum of distances between this point and the two foci will be the same as the sum of these two distances. D sub 1 plus D sub 2 equals D sub 3 plus D sub 4. The sum of distances stay the same. The sum of distances stays the same, corresponding to the fact that the string does not change in its total length. The sum of these distances does not change. It remains constant. But what is that constant? How long is this string? So why is this true? Why this formula? Let's say that we put our marker over here at this west point for the ellipse. Now, remember, the total length of the string is equal to the sum of the distances between this point where the marker is and the two foci. So the total length of the string is given by the length of this red line segment and the length of this green line segment. The distance from this point to this focus plus the distance from this point to this focus. But what is that total length? Well, by symmetry, I can move this over here. And we find that the total length of the string by symmetry is given by the major axis, 2a. The length of the string is 2a. So the length of the string, the total length of the string, is given by the major axis. All right, now let's say that we move our marker from here to here at sort of the north pole of this ellipse. Here's our marker now. The distance from this point to this focus is the length of this red line segment. The distance from this point to this focus is given by the length of this green line segment. By symmetry, these distances, these lengths are equal. Now remember, the total length of the string, the length of the red line segment plus the length of the green line segment is 2a, which means that we have a length of a for the red piece of string, and we have a length of a for the green piece of string over here. The 2a is split evenly like so. The center of the ellipse is here. All right. And let's consider these other sides. So let's connect the two foci here. And let's bring in this semi-minor axis. All right, now let's label, let's say the triangle here with the red hypotenuse. Remember, B here is the semi-minor axis. That's the distance from the center to this north pole over here. C, remember, is the distance between the center and this focus. So according to the Pythagorean theorem, what do we have? According to the Pythagorean theorem, we have, we have the following relationship. We have b squared plus c squared equals a squared. B squared plus c squared equals a squared by the Pythagorean theorem. So the Pythagorean theorem is the basis for this formula, but it looks a bit different. Solve for c squared now. Solve for c squared, okay? In order to do that, we subtract b squared from both sides, and lo and behold, b squared minus b squared, that's 0. They knock each other out. We have c squared equals, look at this, a squared minus b squared. C squared equals a squared minus b squared. Here's a nicer form of the formula. C squared equals a squared minus b squared. So it does come from the Pythagorean theorem, but there's a minus sign, not a plus sign. Okay. It helps indicate the fact that c is less than a. C squared is a squared, but you take away b squared. C is less than a. The distance between the center and either focus is shorter than the distance between the center and either vertex. C here is less than a, which is this over here. So that's why this formula works. Pretty cool.
Okay, I remember when Professor Pat McGeek showed this, I thought that was really cool. But remember, that's a minus sign there, not a plus sign, because c squared is less than a squared. I misstated that earlier on a previous video. C squared is less than a squared. C is less than a. All right. Okay, that's a minus sign, not a plus. Okay, let's proceed. I think the next one is a required video.
Grammarly does more than
now I know what this is. This is a video. I'm going to pause this. Okay, so again, this is an optional video, but I'm describing the other conic sections in greater detail.
Hi, everyone. Here's some optional but cool notes about conic sections. We're going to talk about some cool properties here. Now, let's go back to talking about parabolas. And let's talk about the locus or geometric definition of a parabola. Before we've talked about the locus definition of a circle, a set of points equidistant from a fixed point called the center, and the locus definition of an ellipse, where we consider the set of points whose sum of distances from two fixed points called foci, that sum remain the same, a constant. But what's the locus or geometric definition of a parabola? Now, an ellipse had two foci. A parabola has one focus. And we also need to talk about another line called a directrix. So for example, here's our old friend y equals x squared, a parabola opening upward, the classic one. Now, a parabola consists of all points that are equidistant between a fixed point, called a focus, and a fixed line, called a directrix. So for example, consider this point on the parabola, y equals x squared. The distance between this point and the focus is equal to the distance between this point and the directrix. These distances are equal. The parabola here consists of all points that have equal distance from the focus and from the directrix. If you look at y equals x squared itself, right, the vertex is at the origin. The vertex is the most special point on the parabola. The vertex is the point that's closest to the focus. The vertex has distance 1/4 from the focus. So the focus here has coordinates 0, 1/4. Again, that's for the parabola y equals x squared specifically. And since the origin here, since this vertex has to be equidistant from both the focus and the directrix, that means that the directrix has equation y equals -1/4. That's true for the parabola y equals x squared. Let's consider a more generally shaped parabola. Let's consider y equals ax squared, where a is positive. So for this parabola, the focus is 1/4a units away from the origin here, the vertex. The directrix has equation y equals the opposite of that number here. So that's the locus definition of a parabola. Now, more interesting actually is and also there's a video here, not mine, which describes how to construct a parabola using these ideas. Now, even more interesting though, is the idea of reflecting properties. the reflecting property of a parabola. So consider this parabola. It has a fixed point called the focus, and here's the reflecting property. Let's say that light rays emanate from the focus. Here's the focus F. Let's say that light rays emanate from the focus, like so. How do the light rays reflect off of the parabolic surface here? They reflect off in parallel rays. The light rays reflect off the parabola in parallel rays. Now, if you take a parabola and you revolve it about an axis, you get something called a paraboloid. That's the three-dimensional analog of a parabola. And guess where you see these things on your car? If you're still using your car, not funny. Where do you see paraboloids on your car? How about headlights? This property allows the headlight to shine as brightly as it can, since the rays of light from the focus, they're being reflected off in parallel rays. That's kind of the idea. Now, what's the corresponding reflecting property for ellipses? Right. Well, if you enjoy playing pool or golf, then you love ellipses. So imagine that you have a perfectly frictionless surface and a perfectly elastic boundary that's elliptical. So let's say that you're playing pool or golf. Let's say golf, miniature golf. How can you impress your friends who don't know math? Well, you can put the hole on your little miniature golf course at one focus of the ellipse here, this elliptical playing field, and then you put the ball at the other focus. And the idea is that regardless of which direction that you hit the ball in, right? Regardless of which direction you hit the ball in, if the ball reflects off that elliptical surface, is perfectly elastic here, right? It's going to fall into the hole. So if the ball's at one focus, it'll reflect off the ellipse, and the ball will fall into the hole here at the other focus. Now, this has many applications. This reflecting property for ellipses has a lot of great applications. Again, this is for ellipses, of course. In fact, John Quincy Adams, the former president and congressman, John Quincy Adams, when he was in Statuary Hall in the US Capitol, he would eavesdrop on his political rivals by basically telling his rivals, hey, why don't you stand over here? It's a nice view and all. So his rivals stand over here, and then at one focus, and then above the other focus, he might be standing on a part of balcony above the other focus. He'd be able to hear the conversations of his rivals better because of the reflective properties of this elliptical boundary. Okay, a Statuary Hall was elliptical in shape. So his rivals would talk basically at this point. He'd be up in the balcony, maybe over this focus over here, and he could hear his rivals pretty well, eavesdropping. That's pretty cool, but there are actually serious medical applications as well. Something called lithotripsy. Lithotripsy is used to destroy kidney stones. The idea is that your kidney stone is placed at one focus for this elliptical boundary, and then sound waves emanate from over here, reflect off, hit the stone, and break it up. It's a very non-invasive way of breaking up kidney stones, and this is used, lithotripsy. Ellipses, by the way, have other very important applications. For example, you're standing on one. The Earth. Kepler's laws of planetary motion, 1609. Johannes Kepler. He was the one who said that planets revolve around the sun. And that in and of itself was a controversial idea, right? We got that from Copernicus as well. Planets revolve around the sun with the sun at one focus of an elliptical orbit. Planets and comets go around the sun in elliptical orbits with the sun at one focus. And by the way, in terms of velocities through space, planets sweep out equal areas in equal time. So if the planet is close to the sun, then it moves faster. If the planet is far away from the sun, it moves slower. Bear in mind, for this kind of eccentric orbit, the planet's going to be a lot colder out here than over here. Okay, the Earth doesn't have quite that level of extremes. We're circular enough. Comets, by the way, can have very eccentric orbits. Okay. Oh, and by the way, they're not just elliptical. There's a study that showed that when you consider comets that were discovered before 1970, about 48% had parabolic orbits, only 40% had elliptical orbits, and 11% had hyperbolic orbits. We'll talk about hyperbolas later on. Halley's Comet has an eccentricity of 0.97, very eccentric. Even more eccentric, Kohoutek, about 0.999925 or something like that. So comets can have very, very, very eccentric orbits, very, very elongated, okay, with the sun at one focus. So it's really quite an event when the comet comes around and meets and comes around the sun, the focus here. Usually it's far away. All right, we'll talk about hyperbolas more later on. But ellipses, a nice reflective property. If you enjoy pool, like a pool table, right? A pool ball here, hole here. Really more like golf, miniature golf. Miniature golf is a better example because pool tables don't work like that. Also, if you're eavesdropping, like John Quincy Adams. Lithotripsy, if you have kidney stones, which are painful. Kepler's laws. Planets, comets have elliptical orbits, or conic orbits in general. Ellipses. Fortunately, the Earth is on an elliptical orbit. If we were on a parabolic or hyperbolic orbit, I think we're in trouble. We're moving away from the sun. All right. Okay, so we're going to talk more about hyperbolas, these guys, next time, and talk about some of their properties.
Okay, so once again, on 10.4, I know I have a couple of problems on 10.4. They're additional though, so you could say it's another optional section, but really we're supposed to cover hyperbolas in this class. So try to focus on hyperbolas. Okay, you're going to see them later.
Hi everyone. In section 10.4, we'll talk about hyperbolas. Really, on a final exam, I would only require people to know two things about hyperbolas. And your homework on 10.4, notice those were both additional problems. They're optional. But even though many of these ideas in 10.4 are optional, it's good to go over them, and they're good ideas. All right. So remember, there are four types of conic sections: circles, ellipses, parabolas, and now hyperbolas. And actually, we have seen hyperbolas before. On Desmos, remember the graph of y equals 1 over x. This was a hyperbola, a graph with two branches. In this case, we had branches in quadrants 1 and 3, and this hyperbola had two asymptotes, namely at the x-axis and at the y-axis. In fact, we can think of this as a rotated hyperbola. Y equals 1 over x is a rotated hyperbola. The hyperbolas you normally deal with are either horizontal, like this guy, or vertical, like this guy. And bottom line, these are the only things that I would need people to know for a final. The graph of x squared minus, not plus, like for a circle, x squared minus y squared equals 1, looks like that. It's a horizontal ellipse, opening horizontally.
Hyperbola.
Y squared minus x squared equals 1 is the vertical ellipse, this graph here, which opens vertically.
Again, hyperbola.
So as far as the final material goes, that's all I need people to know. But let's talk more about hyperbolas. Again, hyperbolas have two branches. It's the only one of the conic sections that has two branches. Here, one branch over here, one branch over here. On the vertical ellipse, one branch opening up, one branch opening down. So either left and right or up and down in terms of how they open. Now, let's talk briefly about the locus definition of hyperbolas, the geometric definition. So we talked about the locus definitions for circles, ellipses, and parabolas. Now, the locus definition for hyperbolas is similar to the one for ellipses. Remember, the locus definition for an ellipse said that an ellipse consists of the set of all points whose sum of distances from two fixed points, which we call foci, remains the same. The sum of distances remains constant, remains the same for all points on the ellipse. Now for hyperbola, it's similar, but instead of the sum of distances being kept constant, it's the absolute value of the difference of the distances. The absolute value of the difference of the distances. So for example, let's say that we have two foci. We do have two foci. Let's say over here and over here. The two foci are sort of eaten by the two branches. Right? Now let's consider a point on the hyperbola. Let's say this point on this right branch of the hyperbola. Consider the distance from this point to this focus, and also the distance from this point to the further focus over here. Now, the difference between these distances will stay the same for the various points on this branch of the hyperbola. Okay. If you consider this point over here, draw this point over here. All right. Consider its distance from both this focus over here and this focus over here. Again, the difference in the distances will remain constant on this branch. We talk about absolute value because if you consider, for example, this point over here, consider this point over here. Okay, it's closer to this focus. Its distance from the other focus is over here. Okay. But again, the absolute value of the differences, the absolute value of the difference of the distances will stay the same. The longer distance minus the shorter distance, that'll stay the same. We talk about absolute value because sometimes the longer distance is to this focus, sometimes it's to this focus. But bottom line, the longer distance minus the smaller distance will stay the same for the points on both branches of the hyperbola. That's the locus definition. Now, what's the reflective property? And this has real practical application in the military, in navigation. So let's consider this point over here. What's the reflective property? The reflecting property. So consider this point over here. Now, once again, let me draw the two foci. So I'll draw the two foci again. Let's say the foci are over here and over here. Let's say that we aim a projectile towards this focus over here. We aim a projectile towards this focus over here. But it doesn't make it all the way. It doesn't make it all the way. It hits this hyperbolic surface. And from this point on the hyperbola, it's reflected. And the way it's reflected is that it's then directed towards the other focus. It's directed towards the other focus. So that's the reflecting property of a hyperbola. Okay. Actually, when I was talking about the applications in navigation, that was more towards the locus definition than the reflecting property. Let's go back to the locus definition. Let's go back to the locus definition. What's the application to navigation? All right, so consider a point on the hyperbola. All right, again, we consider the foci over here, one focus over here, one focus over here. All right. Property of hyperbolas, the difference in the distances remains the same. Okay, now what's the application in navigation? And in fact, this is an idea used in LORAN. LORAN, L-O-R-A-N, short for long-range navigation. This is a Wikipedia article. Not that I always look to Wikipedia. Okay, was a hyperbolic radio navigation system developed in the United States during World War II. By the way, telescopes use ideas of hyperbolas as well. Now, what's the idea here? Again, if you consider the various points on this branch, this particular branch of the hyperbola, remember, the difference in the distances from the two foci will remain the same. Now, how is this applicable in, say, LORAN or in, say, navigational applications? Okay, let's say that at the two foci, we have tracking stations, right? And let's say that this tracking station on the right at this focus hears an explosion out at sea 5 milliseconds before this tracking station does. Based on that information, you can model a hyperbolic curve. And basically, based on that information alone, the fact that the tracking station on the right here at this focus heard the explosion 5 milliseconds before this tracking station at the other focus, we know then that the explosion, or we can figure out that the explosion happened somewhere along this hyperbolic branch. Okay. Because remember, this hyperbolic branch consists of all points whose difference in distances from the two foci is the same. So that corresponds to the fact that, that this tracking station heard the explosion 5 seconds before this tracking station did.
Or milliseconds.
And that's a key application of hyperbolas in navigation, LORAN, okay, tracking explosions. All right. Now, back to the math. I'll erase these here. Back to the math. So this here...
by the way, before I don't know if I mentioned this in the videos, but you remember when we were losing all those Malaysian Air planes? You may have noticed that the search path for where the planes may have crashed, they fell in these huge swaths, these curves. I think they were hyperbolic curves when we were trying to locate those downed Malaysian airplanes.
Is the graph of x squared minus y squared equals 1. So this is a horizontal hyperbola. It's a hyperbola that opens to the left and to the right. Okay, now one way that you can tell that it's a horizontal hyperbola is that we have the x squared term over to the left of the minus sign, where the y squared term to the right of the minus sign equals a positive number. And in standard form, we want a 1 there. Okay. Bear in mind, if that's a negative 1, we have to mess with the equation. But if you have x squared minus y squared equals 1, that's a horizontal hyperbola. One way to see that is that if you look for intercepts, all right, the x-intercepts are where y equals 0. So if you plug in y equals 0 and you kill that term, you get x squared equals 1. That means that x equals 1 or negative 1, and we get 2 x-intercepts. But what about y-intercepts? What if we let x equal to 0 and get y-intercepts? The opposite of y squared equals 1, there are no real solutions for y. So notice this hyperbola has no y-intercepts over here. The asymptotes, by the way, the lines that these branches approach in the long run, we have y equals x over here, and y equals the opposite of x over here. Desmos verifies that. So looking over here, here's a graph of x squared minus y squared equals 1. It's a horizontal hyperbola. Notice we have 2 x-intercepts at 1, 0, and at negative 1, 0. Okay. And in fact, these are the vertices of the hyperbola. They're like turning points. These are the vertices of the hyperbola. Y equals x is one line that the hyperbola approaches in the long run. Y equals the opposite of x is another line that the hyperbola approaches. They form an x. The two asymptotes form an x that go through the center of the hyperbola, which is at the origin. The center is in between the two vertices. In a way, it's outside the hyperbola. Remember, an ellipse sort of contains its center. A hyperbola does not contain its center. Okay, these two branches do not eat the center here. Now, over here, y squared minus x squared equals 1. All right, here we have a vertical hyperbola that opens up and down. Again, in this class, we're not going to rotate these things 45 degrees or anything, right? That's for Math 151. Now, we know it's a vertical hyperbola because this equation is of the form, okay, the y squared term is to the left of the minus sign, okay, the x squared term is to the right of the minus sign, equals a positive number here. We want a positive 1 here for standard form. Similarly to before, notice that the intercepts, we have intercepts of one type but not the other. Okay, we have y-intercepts. When you set x equal to 0, y squared equals 1, so y equals positive 1 or negative 1. Here are the y-intercepts. They're also the vertices of the hyperbola. But if we try to look for x-intercepts, when we set y equal to 0, well, this has no solution for x. So there are no x-intercepts. The asymptotes are the same as before. Y equals x and y equals the opposite of x. So I'm flashing the horizontal hyperbola here, x squared minus y squared equals 1. Here, this is y squared minus x squared equals 1. It's a vertical hyperbola, but we have the same asymptotes, the same x representing the two asymptotes. The intercepts are y-intercepts this time, vertices 0, 1 and 0, negative 1. Putting them all together, both this horizontal hyperbola and the vertical hyperbola have the same asymptotes. It's a very nice picture here. If you want to put in all the vertices, 1, 0 and negative 1, 0. Big happy family. These two hyperbolas, the common asymptotes, and the intercepts or vertices. All right. Now, again, I only required you for the final to know the graphs of x squared minus y squared equals 1, a horizontal hyperbola, and y squared minus x squared equals 1, a vertical hyperbola. In the next video, a bunch of optional notes, but some interesting extensions. Next time.
Okay, now before I get to more details on hyperbolas, and yes, the first part of these lectures, I admit, they're not required for the homework, but they're part of your required knowledge moving on. You have to know about conics. Now I'm going to describe how to draw hyperbolas in general. Before I get to that, I want to get you into the rhythm here, and this is relevant. It's a little clip from Scarface. Hyperbolas. There's another rhythm.
So on hyperbolas, on my Math 141 final, I mostly wanted people to remember x squared minus y squared equals 1 opens along the x-axis. Notice there's an x squared in front here, whereas y squared minus x squared equals 1 opens along the y-axis. Notice the y squared is in front here. Again, flashing, here's x squared minus y squared equals 1, horizontal, opens along the x-axis. Here's y squared minus x squared equals 1. In purple, opens along the y-axis, vertical. I'm now going to look at more general notes on hyperbolas. This is optional beyond this stuff over here. All right, remember that hyperbolas have two branches, and you get a hyperbola when a plane intersects a cone in the two branches. All right. And it does not go through the center. If you go through the center, you get a degenerate hyperbola, the intersecting lines. But in general, you would have two branches that go like that, a hyperbola. Again, here are some examples here. Also, y equals 1 over x, where the coordinate axes were the asymptotes. We talked about the geometric locus definition, which told us why we use hyperbolas so that tracking stations can figure out where an explosion may have taken place. If this tracking station heard an explosion, say 5 milliseconds before this tracking station. Also, remember when Malaysian Air lost some airplanes? You might have wondered, why was it that in the news you saw these big hyperbolic branches? Oh, we think the plane may have crashed somewhere along this branch. like this very wide branch over here. Okay, well, it's because of these principles. All right, some terminology here. So the center of the hyperbola, unlike an ellipse, which kind of eats its center, all right, hyperbola does not eat its center. The center is in the midpoint. It's in the middle between the two vertices over here, the two sort of turning points for the hyperbola. Right. The foci are actually further away from the center than the vertices are. So this thing really is turned inside out from an ellipse. Okay, remember, for an ellipse, the foci were closer to the center than the vertices were. Right. So A, the distance between the center and each vertex, same as for an ellipse. C is the distance between the center and each focus, same as for an ellipse. But now for an ellipse, C was less than A for an ellipse. For hyperbola, C is greater than A. Okay. And later on, this will mean, by the way, that the eccentricity will be greater than 1. Okay. It's between 0 and 1 for an ellipse. Now, normally when we draw hyperbola, think Scrooge, bah humbug. First you draw a box, then you draw the asymptotes for the hyperbola, then you draw the actual hyperbola.
That's Scarface.
Bah humbug. Now, how do you draw the box? Well, first you find out where the center is, right? And we need to know what A and B are. A, again, is the distance between the center and either vertex. And of course, the vertex is actually on the hyperbola. The two vertices are on the hyperbolic branches, over here and over here. B is the distance between the center and these points on the box. These points help you draw the box. They're not on the hyperbola. So you want to draw the box with that as the center of the hyperbola, and that passes through these 4 points like so. These points are the midpoints of the 4 sides. Okay, a box, it can be a rectangle or a square. And the asymptotes are drawn as dashed lines through the diagonals of the box. C, again, is the distance between the center and each focus. All right. Instead of a major axis, we have a transverse axis, 2A, connecting the vertices. The conjugate axis is 2B. And by the way, there's no guarantee that A is greater than B, as it was for an ellipse. All right. Now look at this. What's the relationship between C and A? Notice that C is bigger than A. The foci are further from the center than the vertices are. C is greater than A. Look at this equation, this formula. C squared equals A squared plus B squared. It looks more like our classic Pythagorean theorem. Remember, we had a minus sign here for ellipses. Okay. If the center is at 0, 0, here's standard form for the equation of hyperbola that opens along the x-axis. It's horizontal, and the center is at the origin. X squared over A squared minus Y squared over B squared equals 1. Remember, for an ellipse, we had a plus sign there. And bear in mind, A squared is always the denominator on the left. It doesn't matter who's bigger, who's smaller. A squared always corresponds to the denominator on the left, assuming that the signs are appropriate. Positive, negative, positive. Right. For Y squared over A squared minus X squared over B squared equals 1. A squared is on the left. This time the Y squared term is on the left. We have a vertical ellipse. So for determining whether the hyperbola is horizontal or vertical.
I keep saying that. I keep saying ellipse when I mean hyperbola. It's a vertical hyperbola.
You're looking at whether the X squared term or the Y squared term is on the left, assuming that the signs are correct here. Positive, negative, positive. All right. We have equations for asymptotes. The key idea is the slope is rise over run, right? The slope is rise over run, and these are going to go through the origin. If the center is h comma k, we translate. We substitute x with x minus h. We substitute y with y minus k. Okay, it gets a little confusing here because in number 2, you substitute y with y minus k, the second number, the second coordinate. That translates. And the asymptotes are translated in a similar fashion. Eccentricity, E is C over A, like before, for an ellipse. This time C is greater than A. It's kind of top-heavy. E is greater than 1. So, for example, here, the eccentricity is 2 for this ellipse. For this hyperbola. The eccentricity is 10 for this hyperbola. They look like parallel lines. All right. So let's say that you're given an ugly equation for hyperbola. A hint is that the y squared and x squared terms are on the same side, but have different signs for coefficients. We can group terms, group the y stuff and the x stuff. I would recommend putting a plus sign in the middle, though, because if you put a minus sign, you're in danger of messing up signs here. So separate with a plus sign, that's safer, all right? Non-zero constant on the right. Complete the square. compensate as appropriate.
Okay, and by the way, what I'm doing here, I'm not having you do this on the homework, but I want to give you an overview. You may be called to do this in Calc 2, for example, but this is just an overview.
Balance the equation as appropriate. We now have PSTs over here and over here. Factor them. Right. Divide by the right side, so we get a 1 on the right side. Right. That's in standard form. The y square stuff is on the left, so it's going to be a vertical ellipse.
Hyperbola. I keep doing that, hyperbola.
Opening up and down. The center makes the left side 0. Be careful, x equals -2 over here. Y equals +6 over here. Be careful of the order. Right. A squared is on the left. A squared is 4, so A is 2. B squared is 1, the right denominator, so B is 1. A is 2, B is 1. C squared is A squared plus B squared. We get that C equals √5. We've talked about asymptotes. You can get their equations. To graph the hyperbola, here's the center. Right. Draw the box, A equals 2. It's a vertical hyperbola, so you go up for this vertex, go down for this vertex. A equals 2, B equals 1. That gets you over here and over here. You get these points here. Together, the vertices and these two other points help you draw the box. You draw the asymptotes. Through the diagonals of the box is a vertical hyperbola. The vertices we found, they're like the turning point, sort of. You can also find the foci. You also go up and down for the foci from the center for a vertical hyperbola. This time the foci are further from the center than the vertices are. So that's how you would graph a hyperbola, right? And we've talked about applications. Again, this was all optional, but it all makes sense. Next time, polar coordinates and polar curves.
Actually, I have an intervening video here about a topic I should cover. So what we're going to do is, let's see, it's 8 o'clock. That's good. Okay, so I have this short, like 8-minute video on parametric equations and curves. Again, it's an optional topic. So this first half of the class was basically optional, but we had to cover this stuff in this class. So I'm trying to be nice to you by not giving you homework, not assigning you homework, but we had to at least discuss these ideas. So I'll do this video and then we'll take a 10-minute break and then we'll get to the nitty gritty of stuff you're going to see on the homework. All right. So we'll do this and take a break. This is a new video.
Hi, everyone. Let's briefly discuss parametric equations and curves. For example, let's consider this parameter t, which represents time in seconds, say, or the central angle of this circle, this unit circle, in radians. We can describe the motion of this red particle using these parametric equations. X equals cosine of t and y equals sine of t, where t is allowed to vary over the reals, all reals. So think of t as a time parameter. As time progresses, this particle revolves counterclockwise around this unit circle. And we must indicate the orientation, that is the direction of this particle along the circle, by an arrowhead, like so. Now, we can eliminate the parameter in these equations by considering the classic Pythagorean identity. Cosine squared t plus sine squared t equals 1. Well, x is cosine of t, so cosine squared t is x squared, plus y is sine of t, sine squared t is y squared. We get x squared plus y squared equals 1. And the graph of that is the unit circle. However, we lose something as we eliminate the parameter. What do we lose? We lose our sense of direction. We lose our sense of orientation. So that is a price that we pay when we eliminate the parameter, although we do recognize the equation of the unit circle here. It makes it easier to graph. Now, sometimes there are restrictions. So for example, let's say that instead of allowing the parameter t to vary over all reals, let's say that t is only allowed to go from 0 radians to pi radians. If that's the case, what part of this curve do we pick up? We only pick up the top half of the unit circle. We indicate orientation again. And when we eliminate the parameter, we again get x squared plus y squared equals 1. But since we're only picking up the top half of the unit circle, we need to put a restriction. For example, y has to be non-negative. We pick up only the points on the curve where y is non-negative. Now, instead of these, let's say that we have the following parametric equations. How about x equals 3 cosine of t and y equals 2 sine of t? Or again, we allow t to vary over all reals. Presumably t is increasing in value. Time progresses. Now let's solve for cosine of t and sine of t. So we get cosine of t equals x over 3 here. Sine of t equals y over 2. But we still have this basic Pythagorean identity we can work off of. But this time we have, when we eliminate the parameter, we have x over 3 all squared, that's cosine squared t, plus y over 2 all squared, that's sine squared t, equaling 1. Again, we're appealing to the basic Pythagorean identity here. Cosine squared t plus sine squared t equals 1. We get x squared over 9 plus y squared over 4 equals 1. And that's the standard form for a what centered at the origin. That's the standard form for an ellipse centered at the origin. It's horizontal because the larger number is under the x squared stuff. A equals 3 equals 2, centered at the origin. And again, the curve here is oriented counterclockwise. The particle travels counterclockwise along this ellipse. Now, what about something more basic? How about a line segment? For example, how do we parameterize a line segment that goes from 1, 2 up to, let's say, 4, 6? Here's the initial point, here's the terminal point. Consider this directed line segment. Looks like a vector. In fact, we can think of this as a representation of the vector 4 minus 1 is 3, 6 minus 2 is 4. This is a representation of the vector 3, 4, represented as this directed line segment. Now, how can we parameterize this directed line segment? X equals what? Y equals what? Let's let t vary between 0 and 1. So when t equals 0, we start at the initial point, x equals 1, y equals 2. At the initial point, that corresponds to time t equals 0. And we're going to let the terminal point, 4, 6, correspond to time t equals 1 second. So here's the direction vector 3, 4. The trick is we put plus 3t over here for x and plus 4t over here for y. Then when t equals 1, we get x equals 1 plus 3, or 4. When t equals 1, we get y equals 2 plus 4, or 6. So as t varies from 0 to 1, as t goes from 0 to 0.1, 0.2, 0.3, 0.4, and so forth, up to t equals 1, the particle is traveling from the initial point up to the terminal point, and t varies from 0 up towards 1. You can eliminate this parameter. For example, you can solve for t. T equals x minus 1 all divided by 3 over here. Solve for t. T equals y minus 2 all over 4. A horse is a horse. T equals t. You can equate these equal to each other. So we get x minus 1 all over 3 equals y minus 2 all over 4. And then maybe solve this for y. This here is an equation for this line segment. We do need to restrict it though. So x, for example, is restricted from x equals 1 to x equals 4. Okay, we don't get the entire line, we're only getting a piece of the line. And again, this equation loses orientation, but we know the orientation for this parameterization. You'll see this stuff later on.
And in fact, we're going to take a break, and that stuff with orientation, we're going to see with the required stuff after the break in what I call 10.8. Okay, so let's go and take a break now. I have 8:09. Let's take a break until 8:20. Okay, so let me. Okay, so let's come back at 8:20. Okay, mute now, and then we'll unmute and record. Mute now. I'll see you at 8:20, and we'll get to the real nitty-gritty stuff that's really going to help in Calc 2. So definitely come back. Definitely. All right. Okay, so before the break, I did an overview of topics that aren't so much on the required homework. They're not really on the required homework, but they're topics that we needed to cover in this class. And more than anything else, I want you to remember that these are here. I mean, these videos will be available to you if and when you take Calculus 2. So if you see these kinds of topics like parametric curves or hyperbolas, you'll know some videos that you can go back to if you wanted to get a review and overview of some of these topics. Okay, so I did want to do an overview of those topics before the break. Now, the stuff after the break, this is part of the required homework, and these are still things that you're definitely going to see going into Calculus 2, Math 151. All right, so again, more than ever before, go ahead and put questions in chat. Before the break, we're doing overviews, but now you might want to focus more on questions in chat. Let's proceed with some required stuff. All right.
Hi, everyone. Let's continue on with chapter 10. So let's say that you're standing at a palm tree at the origin here. You dig underneath the tree and you find some instructions, a treasure map, that are meant to take you to a point out in the sand where you can dig and get concert tickets for your favorite musical band, once we're after this whole mess with the virus. So here's the question for you. What instructions can get you from the origin over to this point over here? What are some examples of pairs of bits of information that the treasure map could give you to get you from the point at the origin to this point over here where the tickets are? Well, the treasure map could give you instructions such as go 3 meters east and 4 meters north, something like that. In which case, the treasure map would be giving you Cartesian or rectangular information. And basically, the coordinates of this point would be 3, 4. That's a Cartesian way of looking at things. But is there another pair of bits of information that could get you from the origin to the tickets? How about this? If the treasure map tells you how far to go to get from the origin to the tickets over here. So it tells you to walk 5 meters, for example. And if the treasure map tells you what else? Because, hey, I mean, well, 5 meters, do I go this way, this way, this way? Which way do I go?
My name is John Darcy.
Like maybe a direction angle, right? A direction angle, which we often denote by theta. Theta could represent a direction angle. The distance from the origin to this point here, we can call r, a polar coordinate for this point. In fact, r and theta represent polar coordinates. This point over here. And that's going to be our topic for today. Polar coordinates. All right. Now, we saw this stuff back in section 6.3 when we were talking about vectors. So look here. We have here a vector v, and we're looking at its position vector representation, where the initial point is at the origin, and the terminal point is the point a comma b, or x comma y. Let's say that this vector is x comma y, all right? And we can represent it as its position vector from 0, 0 to x comma y. A and b are like specific values. All right. Now, we can associate the length of this vector with this notation, or we can just call it r. R is the length of this position vector. It's the distance from the origin, or pole. We can now call this point the pole. The distance between the pole and this point, a comma b or x comma y. And you may remember from section 6.3 that there is a cosine relationship between x and r, and there's a sine relationship between y and r. So from these relationships, we get this, that if you convert from polar to Cartesian, all right, the x coordinate is r cosine of theta, the y coordinate is r sine of theta. The coordinates of this point. In other words, the components of this vector. X equals r cosine of theta, y equals r sine of theta. And often in Calculus 2, Math 151, you go from Cartesian to polar. You actually replace x with r cosine of theta and y with r sine of theta. By the way, notice that from the Pythagorean identities, we get that x squared plus y squared equals r squared, which corresponds to the Pythagorean theorem applied to this triangle here. X squared plus y squared equals r squared. That's used very often to relate this polar coordinate with these Cartesian coordinates. All right, so let's talk more about polar coordinates. So imagine that you have a point here in the plane, all right, the point P. And instead of indicating Cartesian or rectangular coordinates, x and y, let's indicate polar coordinates, r and theta. By the way, it's not conventional to put these in parentheses the way we do with x and y. So I'm not saying that r always comes first and that theta always comes second, but that's the idea, that we can associate a pair of coordinates with this point. An r coordinate, which is the signed distance from the pole, and a theta coordinate, which is the direction angle. A theta is usually assumed to be in radians, all right? Now, notice I said that r is the signed distance between the point and the origin or pole here. Now, if r is non-negative, then this direction angle is as usual. But the thing that's kind of funny is that even though in section 6.3, we assume that lengths, like lengths of vectors, were always non-negative, actually, when you consider polar coordinates, r can be negative. It is legal for r to be negative. That's okay. If r is negative, you're actually walking in the opposite direction from what you expect. We'll talk more about this later on. Also, the positive or non-negative x-axis is now called the polar axis. This corresponds to theta equals 0 for non-negative values of r. Okay, now let's talk about some basic graphs using polar coordinates. Let's go to Desmos. All right, so let's think about this. In the Cartesian or rectangular plane here, right? How do we get these grid lines? Well, we graph, or we have on our grid paper here, we have things like x equals 0, which is the y-axis. We have x equals 1 over here, x equals 2 over here, and we have grid lines lying on these vertical lines. We also have y equals 0, the x-axis, y equals 1 up here, y equals 2 up here. And of course, we could have y equals pi, y equals 4.7, y equals negative numbers, all right? But the idea is that when you draw a Cartesian graph paper, you have vertical lines that corresponds to x equals a number, and you have horizontal lines corresponding to y equals a number, right? Vertical lines, like these guys, x equals a number. Horizontal lines, like these guys, y equals a number, where the variable equals a constant number. So now what does polar graph paper look like? And I have this on the homework set, you'll see. And you could be given this on homework exams. So here in Desmos, notice I clicked on the wrench here. Under grid, if we go from the Cartesian grid over here to the polar grid, this is polar graph paper. Now, what's going on here? All right, now, how do we graph r equals 1? How do we graph r equals 1? And here's a clue. Remember the basic principle of graphing. The basic principle of graphing. The graph of an equation consists of all points whose coordinates satisfy the equation. The graph of an equation consists of all points whose coordinates satisfy the equation. Back in the old Cartesian or rectangular days, you took this for granted. Let's go back again to the Cartesian grid. All right. How do you graph x equals 0? How do you graph x equals 0? It was the y-axis in blue here. Why is that? Because it contains all points. It consists of all points with x coordinate 0, 0, 0, 0, 1, 0, 0.865, all these guys, right? Okay, 0, 1, right? 0, 2, or 2.02, 0, pi, 0, negative 1.58, whatever, all right? The graph of an equation consists of all points that satisfy the equation. In this case, all points with x coordinate 0. But now, what if we go to the polar graph paper? How do you graph r equals 1? What are all the points that have r coordinate 1? The treasure map says r equals 1. The tickets are 1 meter away from where you're standing. What would be your search path? What figure would you trace out with your shovel? R equals 1, that's going to be the unit circle. If the treasure map says the tickets are 1 meter away, then the search path is potentially along this entire unit circle. How about r equals 2? That's a circle of radius 2, centered at the origin or pole. R equals 3, circle of radius 3, centered at the origin or pole. So r equals a constant number, all right? They're going to correspond to circles centered at the origin or pole. What about r equals 0? R equals 0 just corresponds to the dot right here at the origin or pole. Okay, I guess you can't click on points here for coordinates. R equals 0 corresponds to the origin or pole. There's only one point with r coordinate 0, right there. All right. Now, likewise, what if we wanted to consider, before we do that, what about r equals -1? Can Desmos do that? R equals -1. No, Desmos doesn't know this. Actually, r equals -1 has the same graph as r equals 1. It's just that you're looking at the angles from a different perspective. We'll talk about that later. So r equals 1 and r equals -1 have the same graph. We'll talk about that. Now, what about theta equals pi over 4, let's say? Theta equals pi over 4. Now, Desmos doesn't know how to graph that, but you should. The treasure map says, from the origin, the pole, where you're standing, the tickets are at a direction angle of pi over 4 or 45 degrees away from where you're standing. What would be your search path? Now, technically, it would be on a ray. Here's pi over 4. Technically, it would be on a ray, like so. R equals 0 here, R equals 1/2, R equals 1, R equals 2, R equals 3, R equals pi, and so forth. But actually, if you allow R to be negative, and we do, we actually include the whole line that goes to the origin or pole. So theta equals pi over 4, the graph of that is a line. Okay. For theta equals pi over 3, okay, for theta equals pi over 3, for theta equals pi over 3, it would be along here and along here. I'm not drawing it very well, but pi over 3 and also the 4 pi over 3 ray. Remember, these correspond to negative values of R if you let theta be pi over 3. We'll talk about that. Now, by the way, if you wanted to graph these in Cartesian coordinates, okay, let's go back to the Cartesian grid. Right. So theta equals pi over 3, or how about theta equals pi over 4 first, okay? That corresponds to y equals x. Here's the graph of theta equals pi over 4. It's actually graphable if you use Cartesian coordinates, y equals x, right? For all the points here, theta equals pi over 4. Over here, r is 0 at the pole. Over here, r is negative in quadrant 3. You're walking in the opposite direction from where you'd normally go. For theta equals pi over 3, remember, folks, tangent is slope. The slope is the tangent of pi over 3, the square root of 3, all times x. That's the graph of theta equals pi over 3. R is 0 here, R is positive here in quadrant 1, R is negative here in quadrant 3, the opposing quadrant. So what's this idea of R being negative? We're going to talk about that in the next video.
In fact, this whole idea of R being negative, that's a key breakthrough as people enter the Calc 2 class. That's the thing that messes people up. So I want to touch on issues that might mess you up going into Calc 2. Let's resolve these early on.
Hi, everyone. Back to polar coordinates. So what's this deal with R being negative? So here's the idea. Let's say we want to graph theta equals pi over 3. Here's the origin or pole. There, R equals 0. If R is positive, you walk in the expected direction, in the direction of theta equals pi over 3 or 60 degrees. So for example, here, it's easier to draw this in Cartesian coordinates. Desmos doesn't know this is theta equals pi over 3. Let's go now to the polar graph paper and see here. See this green line? Okay, this corresponds to theta equals pi over 3. Over here at the pole, R equals 0. At this point, R equals 1. At this point, R equals 2. On the circle, R equals 2. Bear in mind that these coordinates that you see here are still Cartesian coordinates, right? R equals 3 up here on this circle. So that's fine. Now, if you walk backwards in the opposite direction, that corresponds to R being negative. So if R equals -1, you go in the opposite direction, in the direction of 4 pi over 3. Okay, we associate the angle 4 pi over 3 usually, okay, with this ray going here. It's pi over 3 plus pi. So if your theta coordinate is pi over 3, but your R coordinate is -1, you want this point in quadrant 3. Okay, again, if theta is pi over 3, you think you're going into quadrant 1, but no, if R is negative, you actually want to go into the opposing quadrant, quadrant 3, and you want this point over here at R equals, well, okay, the R coordinate is -1 here, all right? If you're saying the theta coordinate is pi over 3, the R coordinate is -1 over here. Remember, the R coordinate is negative if you're going in the opposite direction from the angle you thought you were going in. If R is negative, you're going in the opposing quadrant. Remember that quadrants 1 and 3 are opposing quadrants, and quadrants 2 and 4 are opposing quadrants. All right. Now, one implication this has is that every point in the plane has infinitely many polar coordinatizations. So for example, well, take the pole at O, the origin. we know that the r coordinate is 0, but theta can be any angle, all right? Think of the pole over here. R equals 0, but we can let theta be 0, pi over 6, pi over 3, pi over 2, whatever, right? Theta can be any angle. You can put in any radian measure here. If r is 0, we know we're at the pole. For example, let's say that you're standing on the North Pole, or you're swimming at the North Pole on Earth. We know you're at 90 degrees latitude, but what's your longitude? What's your longitude? You're at every longitudinal line on Earth. I mean, what's your sense of west and east, right? If you're at the North Pole. If you're at the pole, right, the treasure map is telling you dig right where you are. Don't worry about what your compass is saying, just dig right where you are. Who cares what theta is? So we know the pole or origin has infinitely many coordinatizations in polar, but every other point does as well. For example, let's take this point here, okay, right over here. Okay, where theta is pi over 3 and r equals 2. In fact, let's try to plot that point, okay, in Cartesian. So r cosine theta, 2 cosine pi over 3, okay, which we know is 1/2, right? Comma 2 sine pi over 3, which we know is root 3 over 2, all right? This is convenient if you forgot, but it is the point 1 comma, okay, that's root 3 over 2, square root of 3. Yeah, all right. Okay, so if you forgot your trig values, okay, well, you could take the purple point there if you forgot your trig values. Okay, if you remember, okay, same point here, right? It's 1 comma root 3. So now that's in Cartesian though. These are in Cartesian coordinates. Remember, Desmos only gives you Cartesian coordinates over here, right? In these ordered pairs. Desmos does not give you r and theta coordinates as part of these ordered pairs here. Now, what are the polar coordinates of this point? There are infinitely many ways to assign polar coordinates. We could say that theta equals pi over 3 and r equals 2. Walk in this direction, 2 meters, and you can get your tickets. But now, wait a minute. You can take pi over 3 and you can get any coterminal angle. You can add 2 pi, add 4 pi, add 6 pi. You can subtract 2 pi and so forth. So in fact, you can coordinatize this point P as r equals 2 and theta equals pi over 3 plus 2 pi n, where n is integer. You can take any of these angles. But beyond that, remember, r can be negative. R can be negative. So another way you can get to this point is by looking at it as follows. Okay, let's say that you take the angle 4 pi over 3. That terminal side, that ray, normally goes through quadrant 3 for non-negative or positive values of r. If theta equals 4 pi over 3 and r is positive, you normally walk through quadrant 3 from the pole. But wait a minute, if r is negative, you walk backwards. So another way to coordinatize this point over here is r equals -2, theta equals 4 pi over 3. Again, if theta equals 4 pi over 3, if r were positive, you'd be going through quadrant 3. You'd be going southwest. But wait a minute, r is negative, so you go in the opposite direction. You're going northeast into quadrant 1. So the point here is the same as the point over here. So r equals 2, theta equals pi over 3, gives you the same point as r equals -2, theta equals 4 pi over 3. Again, infinitely many possible coordinatizations of this one point from coterminal angles alone, but also r could be -2. So next up, we're going to use these ideas to graph polar equations as polar curves, a key topic in Math 151, Calculus 2. How can you graph r as a function of theta? Next time.
Okay. So again, the key breakthrough for that previous video, what happens when r is negative? You're drawing in the opposing quadrant. So instead of quadrant 1, you're in 3, or vice versa. Instead of quadrant 2, you're in 4, or vice versa. Any questions? Any questions? Because again, this next stuff is on the homework and stuff you'll see in Calc 2. Definitely preview this stuff. In fact, when you take Calc 2, preview these videos in the second half before you take Calc 2.
Hi, everyone. Let's graph some polar curves. We're going to treat these as polar equations. Now, in our class, you're going to be graphing circles with arrows on them. It does get more complicated later on in Math 151. But for right now, in example 1, let's sketch the graph of the polar equation, r equals 2 sine of theta, where r and theta are polar coordinates. Now, first, I think it helps a lot to graph these as Cartesian coordinates, where r is like the y coordinate and theta is like the x coordinate. So I think it's helpful to first graph r against theta as Cartesian coordinates. So here, we're graphing one cycle of r equals 2 sine of theta. It's your classic good morning graph, where the amplitude is 2. Now, we're going from 0 to 2 pi, and using the frame method, I'm breaking things up into quadrants. The quadrantal angles break things up into 4 quadrants. And these 4 quadrants will correspond to 4 phases. In the basic examples we do in our class, it's enough to look at these 4 quadrants. In general, for the more complicated examples, which I'll discuss later, okay, then we can get a new phase whenever theta changes quadrant. Of course, that's the case in our examples. And then later on, beyond this, watch out for when r changes direction from increasing to decreasing or vice versa. If r changes direction, we need a new phase. Also, if r changes sign, we need a new phase. But fortunately, in our basic examples, like over here, r will change direction and r will change sign only as we cross over quadrantal angles. So it's sufficient to just look at things in terms of quadrants, at least for our basic examples here. So now we're going to trace the behavior of r as theta changes through these phases. In phase 1, in phase 1, theta is increasing from 0 to pi over 2. R is increasing from 0 to 2. So here in phase 1, okay, again, as theta increases from 0 to pi over 2, okay, r is increasing from 0 to 2, meaning that if you imagine a particle that's going to trace out this curve, the particle is going to be moving away from the pole. Okay, moving away from the pole or origin. And because r is basically positive in quadrant 1, all right, then that means that, well, according to theta, we think we're moving in quadrant 1, the particle's moving in quadrant 1, and because r is positive here, in fact, the particle is moving through quadrant 1. I'll put this in purple. Quadrant 1 and moving away from the pole. Now, in quadrant 2, as theta goes from pi over 2 to pi, r is decreasing from 2 to 0. R is getting closer to 0. It might be helpful to think of, is r moving closer to 0 or away from 0? Is r moving towards 0 or away from 0? Okay. And then if this behavior changes, we get a new phase. Okay, so here r is going from 2 towards 0. So as theta goes from pi over 2 to pi, in what we think is quadrant 2, r is decreasing from 2 to 0, meaning that we're moving towards the pole in phase 2. Now, as theta increases from pi over 2 to pi, we think we're in quadrant 2, and because r is positive here, yes, in fact, we are in quadrant 2. The particle is moving through quadrant 2. All right, so let's see what we have so far. First, r increases from 0 to 2. We're moving away from the pole in quadrant 1. Then r decreases from 2 to 0 in quadrant 2. We move towards the pole. So let's look at the graph we get. All right, first using Cartesian graph paper, and then in polar. All right. So again, in phase 1, We think we're in quadrant 1. We are in quadrant 1. R is positive in here, right? And when theta equals 0, R equals 0. When theta equals 0, R equals 0, all right? That means that we start at the pole or origin when theta equals 0. We move away from the pole until when theta is pi over 2, R equals 2. When theta is pi over 2, R equals 2. So we're at this point here, the North Pole. And then as theta moves from pi over 2 to pi, R decreases from 2 to 0. We're moving towards the pole through quadrant 2. And you need to put these arrows on here, at least put one arrow here, indicating orientation. Desmos doesn't do this. You need to put the arrow here indicating orientation somewhere. Basically, we're always going to be going counterclockwise. In polar graph paper, right, again, we start at the pole when theta equals 0, R equals 0. So when theta equals 0, we start at the pole. Again, as theta increases from 0 to pi over 2, R increases from 0 to 2. So we're moving away from the pole. The distance from the pole is increasing. As the angle increases, here's pi over 2 over here, and we're at the North Pole over here. Maybe put the arrow here. You got to put an arrow at some point. And then as theta goes from pi over 2 to pi, it goes from 2 towards 0. We're moving towards the pole. The particle is moving towards the pole. And at theta equals pi, we're at the pole. R equals 0. We're at the pole. We hit the South Pole here. All right. Now, actually, I claimed that we're done. But let's see why that is. Let's verify that. Let's go through phase 3 now. As theta goes from pi to 3 pi over 2, right? R is going from 0 to -2. We're moving away from the pole. Okay, R is moving away from 0. We're moving away from the pole. But what quadrant are we in? See, if theta is going from pi to 3 pi over 2, we might think we're in quadrant 3. That would be true if R is positive, but wait, R is negative. So we're not going through quadrant 3. We're going through the opposing quadrant, quadrant 1. So we're actually moving through quadrant 1 because R is negative here in this phase. R is 0 over here at pi. Okay. So what does that mean? Let's think about this. So in phase 3, we're in quadrant 1, we're moving away from the pole. R is going from the pole to 2 units away from the pole, but in the wrong direction. All right. So we're in quadrant 1. We're retracing the steps here. We're in quadrant 1. We're moving away from the pole until we're 2 units away. So instead of going through quadrant 3, all right, the thing is R is negative in phase 3. So we don't go through quadrant 3. We're actually going through quadrant 1. We're actually going through quadrant 1. So instead of going this way, instead of going on this ray, we're on this ray. Instead of this ray, and so forth. We're retracing our steps. In phase 3, we're retracing our steps. We're redoing phase 1. And likewise, phase 4 will redo phase 2. In quadrant 4, all right, theta is going from 3 pi over 2 to 2 pi. R is going from -2 to 0. If R is approaching 0, we're moving towards the pole. Okay, now in here, we think we're in quadrant 4, but wait, R is not positive, R is negative. So we're not in quadrant 4. I'll do this in green. We're not in quadrant 4. We're in quadrant 2, the opposing quadrant. Remember, 1 and 3 are opposing quadrants, 2 and 4 are opposing quadrants. If R is negative, you flip to the other one, the other opposing quadrant. So again, in phase 4, we're redoing phase 2. We're in quadrant 2, and we're moving towards the pole. We're in quadrant 2. We start off 2 units away from the pole in the wrong direction. We're supposed to be down here, but we're actually up here because R is negative. R is -2. We're at the North Pole. And instead of going like so, we're going like so through these angles. We're going through quadrant 2, not quadrant 4. And the particle moves through quadrant 2, retracing phase 2. So in fact, phases 3 and 4 are just retracing the steps for phases 1 and 2, but we had to check that. And of course, by periodicity, we're just repeating the behavior overall. All right, don't forget your arrow. Okay, you have to put at least one indicating orientation. It will be counterclockwise in our class. Okay, and on a final, I would allow either using Cartesian or graph paper. I'll provide both, basically. All right, so next up, I'm going to talk about how you can figure out it's a circle analytically using algebra and quickly look at another example.
Okay, so it's a matter of wrapping your head around what happens when R is negative, right? And I'm going to explain in the next video why we're getting a circle. Why is it a circle? Any questions thus far? You might want to review these videos, right? Especially before Calc 2.
Hi, everyone. So why is it that as polar coordinates, R equals 2 sine of theta graphs as a nice circle? Well, Desmos says so. Desmos is good at graphing R as a function of theta as polar coordinates. But even then, Desmos fails to put the arrow indicating orientation. Bad Desmos. But Desmos knows that we get a circle. How can we know that? Let's look at this analytically. First of all, is the pole or origin on the graph? Well, the pole corresponds to R equals 0. Is 0 in the range of 2 sine of theta? Does 2 sine of theta hit 0? Yes, it does. For example, when theta is 0. So the pole is on the graph. 0 is in the range, the pole is on the graph. From now on, let's assume R is not 0, and we can multiply both sides by R. R times R is R squared, and then equals 2R sine of theta. Now remember, how do we convert from polar back to Cartesian? What is R squared in Cartesian? And what is R sine of theta in Cartesian? Remember, R squared is x squared plus y squared. And y over here is R sine of theta. R squared is x squared plus y squared equals the 2, and then R sine of theta is y. I'll do this in red. R sine of theta is y. All right, so we have x squared plus y squared equals 2y. Okay, now let's subtract 2y from both sides. Let's get this into the standard form of the equation of a circle. CTS. We group these terms together. Use CTS by adding 1, complete the square by adding 1. If you add 1 in here, you have to balance that out by adding a 1 to the right side. Fortunately, we just have a 1 out here, not a 2 or a 3. So we add 1 to both sides, basically. All right. Factor the PST here. We get x squared plus the square of y minus 1 equals 1. That's the standard form for the equation of a circle. What's its center? What's its radius? For the center, what makes the left side equal to 0? 0, 1. What's the radius? R squared is 1, so R is 1. So here's the data. We have a circle of radius 1 centered at 0, 1. A circle centered at 0, 1, and the radius is 1. In Cartesian, it might look better. All right. However, this analysis does not indicate orientation. This process is sometimes called eliminating the parameters. But one problem with that is that you sometimes lose orientation. This tells you nothing about orientation. Remember that in our class, it's going to be counterclockwise. Put the arrow in. All right. Now, in example 2, let's look at how to graph R equals -2 sine of theta as polar coordinates. Well, it's a similar process. Now, if you first graph r against theta as Cartesian coordinates, you get the good evening graph here, right? And then as theta goes through quadrants 1 and 2, what happens with the actual particle or the actual curve? Well, when theta is in quadrants 1 and 2, where do we graph? R is not positive. R is negative in here, right? R is negative. So we don't graph in quadrants 1 and 2. We graph in the opposing quadrants. We don't graph in quadrants 1 and 2. We graph in the opposing quadrants. The opposing quadrant for 1 is quadrant 3. And the opposing quadrant for 2 is quadrant 4. So in phase 1, we graph in quadrant 3. In phase 2, we graph in quadrant 4. And by the way, why is this south pole point on here? 2 units below the origin or pole. Well, that corresponds to theta equals pi over 2. When theta equals pi over 2, r is negative 2, all right? So when theta equals pi over 2, we graph this way if r is positive, but wait, if r is negative, we graph in the opposing direction. That's probably better to say than the wrong direction. We graph in the opposing direction. We graph in the south direction. The point is 2 units or 2 meters maybe south or below the pole. All right. And then in quadrants 3 and 4, well, r is positive here. We are graphing in quadrants 3 and 4. It turns out that we're just retracing our steps. Phase 3 retraces phase 1. Phase 4 retraces phase 2. Remember to put at least one orientation arrow.
Actually, as a general guide, I might recommend putting an orientation arrow for each phase. When we talk about more advanced examples, you'll see the value of that.
The polar graph paper looks like this. R equals 0, and then r goes towards negative 2. If r is negative, so we're not in quadrant 1, we're in quadrant 3, right? Until we hit the south pole over here, all right? And then in quadrant 2, again, r is negative, so we're actually graphing in quadrant 4 again. We're graphing quadrant 4, all right? In quadrant 3, when theta is in quadrant 3, r is positive, we are graphing in quadrant 3. And when theta is in quadrant 4, r is positive, we are graphing in quadrant 4. We're just retracing the steps. So I'm going to have you graph circles, but the graphs do get more complicated and more beautiful, as we'll see.
All right, so on your homework, I'm asking you to do circles, but hang in there because you really should know this stuff going into Calc 2, the more advanced curves. Questions thus far. Questions thus far. Get some practice with thinking about these things. All right.
Hi, everyone. This video is optional, but it will end with a touching ending. All right, let's try graphing the polar curve r equals 1 plus 2 cosine of theta. First off, we may want to graph r versus theta as Cartesian coordinates using the frame method, Picapia, like in chapter 4, perhaps. And remember, when do we get a new phase? When theta changes quadrant, when r changes direction from increasing to decreasing, or vice versa, or when r changes sign. So over here, it turns out that between 0 and 2 pi, there are actually 6 phases. And beneath, I'm putting the key r values underneath the values of theta where we change phases. All right, so in phase 1, that's straightforward. It goes through quadrant 1, and that's just a single phase because r is decreasing throughout quadrant 1, r stays positive, we're in quadrant 1, it's a single phase. But then phase 2 is short because between here and here, r is positive, but then r changes sign. So when r changes sign, we have a new phase. We're in phase 3 now. We're going to want to find out what a is. That's like a theta intercept or a 0 for r. We want to know where r equals 0. So we're going to find out the value for a here later on. That's where we change phases from phase 2 to phase 3. In phase 3, okay, that takes us up to theta equals pi, which is a quadrantal angle. And remember, when we change quadrants, we have a new phase. So we now go to phase 4. Okay. Also, R is now going from decreasing. R changes from decreasing to increasing. That's another reason why we have a new phase. And then at this 0, when R equals 0, all right, R is going from negative to positive. We're changing phases from phase 4 to phase 5, right? And then at 3 pi over 2, a quadrantal angle, we're changing quadrants. So then we enter phase 6. Phase 6, like phase 1, is a very nice phase. It covers a single quadrant. R is monotonic. In this case, it's increasing. It doesn't increase and decrease. It's just increasing. And R stays positive. So we have 6 phases here. All right. Now, it turns out that we get what's called a limacon with a loop, although you should put a bunch of arrows here to indicate orientation. Desmos knows what it looks like. But let's try to trace this out. Okay. So here's my handwritten version. A limacon, like a snail, with a loop, an inner loop. Oh, and guess what you do in calculus? In calculus 2, you're going to find areas, like the area inside the outer curve, maybe the area inside the inner curve, and so forth. All right. Maybe the area between the outer curve and the inner loop. All right, anyway. So why does it look like that? All right. So in phase 1, okay, R is positive but decreasing. All right. We start with, okay, when theta is 0, R is 3. So we start off here, 3 units away from the pole. All right. But in phase 1, R is decreasing. We have that arrow there. R is decreasing until we get R equals 1. When theta equals pi over 2, R equals 1. At the quadrantal angle, pi over 2, we get R equals 1. 1 unit north of the pole. And then in phase 2, all right, we're in quadrant 2, R is positive, and we're moving towards the pole. R is decreasing from 1 to 0. We're moving towards the pole. It turns out that A is 2 pi over 3. R equals 0 at 2 pi over 3. I'll explain that in a minute. So then at 2 pi over 3, we're at the pole. In phase 3, we start this inner loop. Remember, put these arrows here. For each phase, put an arrow. Okay, that's why I put 2 arrows on the circles before. But here, we really need arrows for each phase. Phase 3, put an arrow, all right? Phase 3, okay, we think we're in quadrant 2, but we're actually in quadrant 4, all right? Because R is negative, all right? And we're moving away from the pole, okay? Until we're 1 unit, R equals -1, 1 unit away from the pole, where we're here. In phase 4, okay, we're moving towards the pole. We think we're in quadrant, we think we're in quadrant 3, but we're really in quadrant 1 because R is negative. We're moving towards the pole. Put the arrow there. B corresponds to 4 pi over 3, as it turns out. B is 4 pi over 3, as it turns out. That's where R is 0. We hit the pole. So phase 4 ends when we hit the pole, when theta is 4 pi over 3. And then in phase 5, okay, from 4 pi over 3 to 3 pi over 2, right? R increases from 0 to 1. We think we're in quadrant 3, where we are in quadrant 3. So we get this piece here with the arrowhead, phase 5. In phase 6, R is positive, increasing from 1 to 3. We think we're in quadrant 4. We are in quadrant 4. Nice big piece of the outer loop here. Put the arrowhead. Wow. And then by the time you get past 2 pi, you're just retracing this thing. 1, 2, 3, 4, 5, 6. I'll do it again. 1, 2, 3, 4, 5, 6. I'll leave this on with a loop. All right, that's not funny. Now, how do we find A and B? Well, R equals 1 plus 2 cosine of theta. Set R equal to 0. Solve for cosine of theta. Cosine of theta equals -1/2. You're solving a trig equation for values of theta between 0 and 2 pi. Where is cosine of theta equal to -1/2? At 2 pi over 3? Hold on. At 2 pi over 3 and at 4 pi over 3. A is 2 pi over 3, B is 4 pi over 3. A is 2 pi over 3, B is 4 pi over 3. That tells us where the loop, where the limacon of the loop, where the curve hits the pole. At theta equals 2 pi over 3, we hit the pole. At theta equals 4 pi over 3, we hit the pole. Okay, that determines where we start and end the inner loop. Okay, sometimes it helps to draw these extensions for perspective, like when r is negative. All right.
It might be more accurate to say when instead of where, when we start the inner loop. You can think of theta as like a time variable.
Now, let's put a slider here. Instead of a 2, what if we have 1.5? Okay, smaller loop. What if that's a 1? That's called a cardioid. It's called a cardioid. That's r equals 1 plus cosine of theta because it looks like a heart, right? It looks like a heart. So it's called a cardioid. What about 0.7? That's called a dimpled limaçon. There's no loop. What if we put a 0 here? That's r equals 1 basically. We get a circle. In fact, you put an a here as like a coefficient for cosine of theta. Add a slider. When a equals 1, we get the cardioid. Looks like a heart, right? If that number in front of cosine of theta grows, we get a limaçon with a loop. Again, going backwards, back to the cardioid. And then if a is less than 1, we get these dimpled limaçons. And then if a is 0, we get r equals 1. That's a circle. And then if a is negative, okay, we're getting in different quadrants here. So you have animations based on the changing values of a. All right. So once again, limaçon with a loop, cardioid, dimpled limaçon, circle, and then in the other direction. Now let's look at this guy. R equals 2 sine of 3 theta. Okay, that's where you have the rapid cycling. You have a short period. 2 power 3 is the period. It turns out that you get everything between theta equals 0 and theta equals pi. 6 phases. R changes from increasing to decreasing. R changes sign from positive to negative. R changes quadrant. Also, R changes from decreasing to increasing. R changes sign. R changes from increasing to decreasing. All right, then we hit pi. 6 phases. Look at this. It goes phases. 1, put the arrows on the phases. 1, 2, 3. R is negative here, right? 4, 5, 6, and then we retrace. It's a 3-leafed rose. R equals 2 sine of 3 theta. Relief rose. Again, put the arrows. Now, what if we, instead of a 3 theta, what if we have a 4 theta? It's not 4 leaves, it's 8 leaves. 5 theta, back to 5 leaves. 6, you have 12 leaves. So the rule is that if you have r equals a sine or cosine of n theta, let's assume a is non-zero. If n is odd, you have n leaves. If n is even, you have 2n leaves. Okay, or you could think of it this way. In both cases, you have 2n leaves, but in the n odd case, you have n leaves overlapping on top of n leaves. So once again, for something like this, n equals 2, you have 4 leaves. Okay, n equals 1, you have 1 leaf in a way, right? N equals 2, you have 4 leaves. N equals 3, 3 leaves. N equals 4, 8 leaves. N equals 5, odd, 5 leaves. N equals 6, even, 12 leaves. N equals 7, odd, 7 leaves. N equals 8, even, 16 leaves. Let's go back to 3. N equals 3. Guess what you do in calculus? Find the area in 1 leaf, and then find the area inside the entire rows. So we end with a romance. I leave you with a rose. Congratulations, that's pre-calculus.
All right, so that's pretty much that. Congratulations. I would like to end with a few fun videos, and we have some time for some questions, though. Now, I didn't have time to play this before, but this is, oh, where is it? Yeah, here it is. I actually met this guy, Professor Art Benjamin from Harvey Mudd College. He was at a convention at the San Diego Convention Center a couple of years ago, where he was doing a backgammon session. And he did this great TED talk about the Fibonacci numbers. I didn't have time to do this last week, but this is a great video. Here's some key clips. It's about 6 minutes. I better pause this. Okay, so we still have some homework to do, right? Okay, so that's pretty much it for today. Again, we have the homework session Thursday, so I didn't mind being a little foolish. On campus, I might have shrunk today a bit, but a lot of good stuff we did today, though. All right. Let's see. Okay, so at this point, I'll go ahead and start off the homework questions you have. So for some of you, I'll see you Thursday. We're going to have a really, really great homework session on Thursday, I'm sure. We'll cover a lot of questions there. And remember, I had here the list of questions that I've covered in previous office hours, right? Previous office hours, previous videos. So I have these already on my YouTube playlist from various weeks. It's in multiple weeks, like either end of class or in separate office hours. I had 3 of them during the Thanksgiving break. I had these 3 during the Thanksgiving break. The others, I think, were more after class, right? So we should have some more now, and then Thursday it'll be a whole session of questions. So no new material on Thursday. It's all you and your questions. All right. So for some of you, I will see you Thursday. You're going to want to see me Thursday, right? Homework is due next Monday. Alex is due next Monday, December 14th. Okay. No more new material, but you might want to see me that extra day Thursday. I also have office hours, right? Make sure Monday too. If you have some questions Monday, I'll have office hours Monday if you want to email me. So some of you I'll see Thursday, hopefully. Okay. In the meantime, do you have any homework questions now for me? I am recording, but if you'd like me to pause the recording, I'll pause the recording. All right. Okay. So let's go. I'll go ahead and hook up the tablet. All right. Yeah, so on December 14th, on Monday, sure. Although you should email me beforehand so that we can arrange a time. Okay. So, because, I'm not going to leave my Zoom room open and then I'm just kind of, because the thing is, if I keep my Zoom room open, then that locks up my laptop. So if you send me a time beforehand, I'll kind of expect that I can hold office hours during the usual kind of early evening, right? I guess on Monday it's 6:30 to 7:45, but I can work that, right? Okay. Let's see. Sorry, a bit of a mess today. Got all these things lying around. All right. All right. All right. So let's see, 8-1. Okay, so let's get this off. All right. Okay. All right. So let's see. First one is what? 8-1-16. A answer is no because the two ones are on top of each other. Oh, okay. So All right, 8116A. Okay, is the matrix in row echelon form? You're correct. The answer is no. Okay, and you gave the right reason too. The reason being that in order to have row echelon form, the leading ones have to go down and to the right. Now, here are the three leading ones. The problem is that for row echelon form, you're not allowed to have two leading ones in the same column. Okay, so the answer is no for A. And if you're not in row echelon form, then there's no way you're in reduced row echelon form either. So the answer to both would be no. Correct. Okay, so your reasoning is correct. All right. Right, 941. Yeah, now 941, that's that whole induction one where, remember I had the Khan Academy link, and I can also discuss that in a moment. They'll take a while though. So I'm going to try to hit some of the shorter ones right now. Oh. I finally found this dongle. It dropped on the floor. Okay, here we go. All right. All right, there we go. There we go. All right. Okay, so okay, so yeah, so the induction one, 941, 918. Okay, I'm just kind of going through through this, then I'm going to remind myself of the induction one. Okay, okay, so let me hit 918 first. Oh, right, these. Okay, so what I'd like to do here is I'd like to do maybe maybe a sample one here, and then I want people to think about this, and I'm sure we're going to do more of these, maybe all of them on Thursday. It's quite possible we might do all these on Thursday, but let me ask you, let's see. Is there one you'd like to look at? Okay, so among, right, so now one number 8 of these, basically pick one. Now the answer to A, this is kind of a recursive thing. I can tell you that the answer to A is n plus 1 all factorial. I can talk about that in greater detail. Okay, but maybe it's more helpful if I do either B, C, or D. Okay, so why don't I do this? Why don't we start with B, and then I encourage you to think about C and D, and I'm sure we'll have the opportunity to do those on Thursday. All right. But these are great ones because these are things that you'll definitely see in Calc 2. And I only lightly covered these in the videos. I covered these in most detail when we did the handshake problem, right? Remember that? Okay, so, whoops. Let's look at B. All right, so this is 9.18B. You sunk my battleship, right? Okay, let me, oh, here we go, yeah. All right. Okay, so I'll do this in blue. All right. Okay. So 9.18B. Okay, and then A, if you understand the answer, you can look at that by example, like plug in n equals 3, n equals 4. See if you can see this by example. And then C and D, it's very likely we'll do these on Thursday. You can ask for them. All right, but let's go to B as a warm-up. Let's do this as a warm-up. All right. Again, key skill in Calculus 2. We have n plus 2 all factorial over n factorial. All right. And in fact, it might even be a nice exercise to plug in a value for n. That might even be a strategy. I'm going to do this in red. Okay, now this is optional, but this might help you think this through. Try n equals 2, for example. All right. So we have 2 plus 2 all factorial over 2 factorial. Let's just get the flavor of this. 2 plus 2 is 4. How do you simplify 4 factorial over 2 factorial? Now, this is not required work. I just want you to kind of think this through. And this will suggest a solution for the general case. All right. What is 4 factorial? a 2t, an algebra 2t asks you, hey, what's 4 factorial? You might think of it in terms of a countdown, right? You might think of it as 4 times 3 times 2 times 1, right? What's 2 factorial? 2 factorial is 2 because it's 2 times 1. And then what happens here? What happens? We can do some cancellations. Here it's not too rough. I mean, 2 divided by 2 is 1. 1 divided by 1 is 1. 4 times 3 is 12. Okay, so that's kind of the flavor of what we have here. But we want to say that this is true for all positive integers and at least 2. All right, so this is like just the basic case. How can we generalize these ideas? All right, and feel free to interject with any questions that you might have. Okay, so over here, and actually in the chat, yeah, you had a better idea there, where we do a countdown, all right? So what's n plus 2 all factorial? Think of it as a countdown. Just like over here, when we have 4 factorial, we start with a 4 and then count down to 1. Over here, we start with n plus 2, which is the largest integer. We're assuming that n is an integer, right? We're assuming n is an integer. So n plus 2 is an integer. This is the largest integer that gets multiplied in the countdown. And then we count down. We go down 1 by 1. Notice that we subtract 1 to get each new entry, each new factor. What is n plus 2 minus 1? What happens when you subtract 1 from n plus 2? What do we get? We get n plus 1, correct? We start with n plus 2. To continue with our countdown, we subtract 1 from n plus 2, we get n plus 1. So this is n plus 2 minus 1. That ends up being n plus 1 as your next factor. I'll do a straight line here. All right. And then let's continue our countdown. What's n plus 1 minus 1? If you subtract 1 from n plus 1, we have n. And then similar to this logic over here, right, what happens? We're going to keep counting down, n minus 1, n minus 2. For now, let's assume that n is big enough, right? So we have all these. And then we end up with 2 and 1, right? But as you've noticed in the chat, what's 2 times 1? That's 2 factorial, right? Well, similarly, what's all the stuff over here in green? What's all the stuff over here? We have 1 times 2 times all the way up to n, or look at this as a countdown, n all the way down to 1, we get n what? We get n, we're multiplying all these factors down to 1, n factorial, which matches up with the guy down there, n factorial. So the general strategy, and then in red, this kind of hinted at it, the general strategy is that we unravel the larger factorial. In this case, the larger factorial is the top expression. We unravel the larger factorial until we get a copy of one of the factorials on the bottom. All right. Very often you'll have one or more factorials on the bottom. So you take the bigger one, unwind it, unravel it until you get a copy of a factorial on the bottom, and you can do some cancellations. Whatever n factorial is, n factorial divided by itself is 1. We're assuming that n is not 0, for example, right? Okay, so then what are we left with? We're left with just 2 factors up here. We're left with the n plus 2 and the n plus 1. Okay, and I would typically accept that, although if I wanted it in descending powers, you can write it out. So this is what? It's a n squared plus 3n plus 2. But that's not the point. I hope you can FOIL, but that's not the point. The point is to get that. Okay, if you reverse the order, that's fine. Okay, it's okay to reverse this order. Okay, so I know that when you simplify this, you get that. And that's a key skill in calculus 2. We get n plus 2 and n plus 1. Just like over here, if you have 4 factorial over 2 factorial, you end up with basically 4 times 3. You get the highest number and then the next guy down. It's like the president times the vice president, right? 4 times 3 is 12. Yes, yes. So B is a good warm-up, all right? C and D, they're just a tiny bit uglier, but the basic principles are the same. You take the larger factorial, expand it out until you cancel out with the factorial in the other part of the fraction. So for example, let me make this final point. On part C, we assume that n is a positive integer. On part C, n is a positive integer, at least 2. Which is the greater factorial? Is it going to be the top factorial or the bottom factorial? Which will be the greater factorial? The top or the bottom? The greater factorial will be the bottom. So you actually want to unravel the bottom. And in your final answer, you're going to have a 1 on top. Don't forget that. So some key warm-ups and tools for 9.1 number 8. And I'm glad you brought that up. I'm glad that we did that warm-up, and I'm sure that we'll do these others on Thursday. If I don't do them, remind me, okay? But yeah, we should do these on Thursday. All right, so let me continue on with the chat questions. I can come back to this. I better save this, by the way. Always good to save your work, isn't it? Okay, so this is was it 9.1 number 8B? Okay, good one to save. All right, so I'll continue with the chat question. I know that there was a question about induction. That's a big one, right? Okay, 8.4, 3B and C. And I forgot which ones I did in office hours, but 8.4. Okay, this one I don't think I did in office hours yet. All right, so this will be our video. And again, without anyone's objection, I'll go ahead and post this as part of the class video. If you want me to pause, I'll pause. Okay, so 8.4, 3B and C. Okay, so now Cyrus's rule involved all those diagonals. B and C involves the cofactor expansion method. And I better get, I'm not going to do it on here. I'm going to do it on separate whiteboards. All right, so I'll label this in green. All right, 3B and C. Okay. Okay, so 8.4, let's start with 3B. Okay, so in 3B, I instruct you to find this determinant by using a cofactor expansion along the second row. So that means that this here is what I call our magic row. Okay, we're going to expand along that second row. Okay, so the determinant we want, I'll write det of B, okay, to denote what we want. We want the determinant of this matrix. All right. I'll go ahead and do this. Okay, you don't have to write this out, but determinant of 1, it might be good for your reference, right? 1, 5, -2, 3, 4, 0, and -1, -4, 3. If you do this, make sure you don't miswrite anything. You might want to double check to make sure that you have the right numbers in the right places. 1, 5, -2, 3, 4, 0, -1, -4, 3, including the signs. So this indicates determinant. You don't have to put the square brackets if you put these vertical bars. It indicates that these indicate that we're taking a determinant of this 3x3 matrix. The result will be a number. Okay, so once again, we're expanding along the second row. All right, we're expanding along the second row. So the cofactor expansion method. All right, so equals. All right. Now, there are 3 pieces we need to look at for each term. So look here, we have 3 numbers along this magic row, right? The 3, the 4, and the 0. So what that means is that we're going to have, in general, 3 terms in the expansion. However, because there's a 0 in that third entry, it turns out that our last term will in fact be a big old 0, and we're happy about that. Okay, because of the 0 there. And by the way, if we had a row of all zeros, the determinant would be 0 right there, by the way. Okay, but it turns out that we just have 2 terms in the expansion that we really have to worry about, coming from the 3 and the 4. Okay, so how do we do the cofactor expansion? And feel free to put questions in chat. I'm looking at the bottom of the chat screen right now. All right, so we have 2 real terms in the expansion. We have 3 in general, but we know the third term is going to be 0. Okay, so we have 2 terms, and each term will have 3 pieces to it. Okay, we're going to need the sign from the Sine matrix. All right. We're going to actually need the magic entry from the magic row in this case. It's a row, right? Yeah, second row. Okay. Make sure you get the right one, right? Okay. So we have the corresponding magic entry here. And then we have the big piece, the determinant of the submatrix. I'll write it out like this. The 2 by 2 submatrix. All right. I'll move these guys down a bit. Well, I mean, let's erase all this for now. The smiley face is cute, but I don't need him. All right. So let's do the first term in the expansion. Now remember the Sine matrix. What do we mean by the Sine matrix? Okay, do that in purple here. Here is the Sine matrix. It goes like this. So we have a 3 by 3 matrix. The Sine matrix goes like this. Okay, it's 3 by 3. This is 3 by 3. Plus signs along the main diagonal. And then it acts like a checkerboard or a chessboard. Left to right, up to down, we alternate signs. So we have plus, minus, back to plus. Over here, that's a minus. It's always a plus on the main diagonal. That's a minus, plus, minus, plus. Now, bear in mind that since we're doing an expansion along the second row, for now, I just care about the signs on the second row. Now in part C, you'll be able to use the signs in the third column, but that's for later. But for right now, if we're expanding along the second row, I just need the signs on the second row. You don't actually need these others as part of your work. All right, so what do we need from our Sine matrix? All right, well, the first entry corresponds to a minus sign. Okay, so I'll put a big ol' negative sign there. That's the sign from the Sine matrix. The corresponding magic entry, that first magic entry, is a 3. I'll put it in parentheses for good measure. All right. And then the determinant of the 2 by 2 submatrix that we get when we delete the row, in this case, it's always this magic row, and the column containing the entry we're looking at. So right now we're looking at the 3. Okay. Well, delete the row and the column containing the 3, and we're going to focus on these 4 other positions. This, and this. These are the 4 entries that go in the 2 by 2 submatrix. The 5, the -2, the -4, and the 3. These are the entries that are left when you delete the row and the column containing the magic entry you're looking at. All right, questions so far? Questions so far? Now, what about the second term in the expansion? Well, again, we still have the second row as the magic row we're expanding along. All right, we're expanding along the second row. All right, but this time we're going to focus on the 4. All right, so what's the deal with that? What's the corresponding sign from the Sine matrix? It's a plus sign this time. The 4 here corresponds to the plus sign here. Plus, we take that 4. I'll put it in parentheses. Then we take the determinant of this 2 by 2 submatrix. Again, we delete the second row, the magic row expanding along. This time we delete column 2, the column containing the magic entry we're looking at. We delete the row and the column of the magic entry we're looking at. We're looking at the 4 right now, staring at them. We're deleting this plus sign, this T over here. And who's left? You don't have to circle, but I just want to make my point. We still have the 1, the -2, the -1 down here, and the 3 over here. You don't have to circle them, but know who they are. The 1, the -2, the -1, and the 3. You might want to double check them. All right. Any questions thus far? Because once you get to here, it's fairly automatic. Any questions thus far? Now it's a matter of remembering the 2 by 2 butterfly. Remember that to take the determinant of a 2 by 2 submatrix, it's done by using the butterfly. Remember? I'll use brown. It's the product along the main diagonal minus the product along the skew diagonal. Same for this. Product along the main diagonal minus product along the skew diagonal. Okay, so let's work this through. Equals. We have -3 times the quantity. I like to write down the products. 5 times 3 is 15. Minus -2 times -4 is 8. But we're subtracting that product. We're subtracting the product along the skew diagonal. -2 times -4 is 8. So it's 15 minus 8. To avoid confusion, I write down the products. 15, and then the minus sign, and then the 8. Of course, if you want to do it another way, that's fine, but show me work. Plus, I got to shrink this a bit because there are captions down here later, right? Okay, plus the 4. Okay, 1 times 3 is 3. Minus, on the skew diagonal, -2 times -1 is 2. Okay. And this is a matter of simplifying this. -3 times 15 minus 8 is 7. Plus 4 times 3 minus 2 is 1. So this determinant was 7. This determinant was 1. -3 times 7 is -21. Add the 4. We get -17. That should be our determinant. Let me verify that. I'll cry if I don't get the right answer. You'll hear a teacher weep. Let's see, which one is this? This is 843. 3B and 3C will have the same answer, right? Ah, yes, I don't have to weep. Okay, and you should show some work. Oh, and don't forget, what about the third term of the expansion? Remember, you had a 0 there, right? So if you're doing your work, you might go, hey, what about minus 0 times? You have minus 0 times, but then you go, wait a minute, it's gonna be a 0 anyways. Who cares, right? Yeah. So it didn't even matter what the submatrix is, right? Because you have minus 0 times whatever. It doesn't matter. Who cares, right? Okay. All right. So that was 3B. So I would like to ask you, okay, now 3C is similar, except that what you're going to do is you're going to expand along column 3. And then the second entry here has a 0. So I want to I have a suggestion for you. Is it okay if you try out 3C and let's do it on Thursday? Yeah, if you have trouble. Yeah. Right. Okay. Yeah. Okay. So I'm encouraging the class to do 3C on your own based on these ideas. You're expanding on the third column. Try it out. Now you're going to get the same number. You still need to get the -17, right? Because the determinant is only one number, right? When I say find the determinant of this matrix, it's going to be just one number. We're just finding it in 3 different ways. Saris's rule, which had those diagonals. Remember those diagonals? I went like this, right? Right. and then 2 cofactor methods. Oh, good. So the one student asked got it, but of course there might be other students in the Zoom room or out there. I'm speaking to the ether. Those of you seeing me on the video, some of you might not have gotten 3C. So if you have trouble with 3C, by all means, we can do that on Thursday. But try to look at my video for 3B just now and see if you can do 3C. You have to kind of tilt your head a bit. Okay, so we can come back to that on Thursday if necessary. And there's still the induction one I want to look at. Okay, and then trying one of 9.3, a group there, and then maybe I'll go back to the induction one. Okay, so 9.3, 3D45B, 3D45B.
Yeah, they're pretty much the same. It's just in different sequences. So
Right. So let me do. How about 4D? Let's do 4D. Okay, and then as I discussed this, then 3 and 5 should be okay from that. Okay, I know what you're saying. So let's try 9.3 4D, and then kind of think about the others. And then as I go over the induction one, if you have a question in chat, or we can do a follow up. Okay, let's do 4D for right now, and we'll discuss later if necessary. All right, save this one. Yeah, I better save this one. 3B. Okay, so this will be 934D. 934D. I sound like a lawyer. Provision 934D. Okay, CCC here. Go back to blue. Or how nice turquoise. There we go. Okay. Oh, okay, so how about 4D over here? Okay. Okay, looking at this sequence here. Oh, okay. So a key bit of preliminary information. This is really key. R equals, so you found R in order to answer part A. Now R, and this is one that is a little tricky to find. Remember, to find R, you can take any, basically you can take the second term over the first term, or I think what might be easier, the third term over the second term. Okay, we could do A sub 3 over A sub 2. It looks like that's going to be the easiest calculation. The third term is 1/2. The second term is 1/3. Here's the way I like to look at it. The top guy is 1/2. If you're dividing by 1/3, you're multiplying by its reciprocal, which is 3, or 3 over 1 if you wish. So R is 3/2. Okay. So I see now what's happening. Yeah, R is 3/2. So right off the bat, we know what's happening. Okay. So I'll give you an example. If I gave you like an exponential function, right, before, and we had like 2, 4, 8, 16, we keep doubling down, right? We know that these would approach infinity. That's pretty clear. It turns out that these guys here, it's not as clear, but it turns out that these terms will also approach infinity. It's not as severe as this, but the multiplier is 1.5, which is too big. The problem is that it's bigger than 1 in particular. So here's the rule. First of all, it is a geometric sequence, right? I say it's a geometric sequence. Here's the rule. All right. The terms, and I mentioned this in the notes, the terms of a geometric sequence approach 0, right? If and only if the absolute value of R is less than 1. And I'm assuming the first term is not 0 itself. Okay, assume first term not 0. Okay, so the terms will approach 0 under these conditions. Otherwise, we have a problem. All right. So D, as n approaches infinity, do the terms of the sequence approach a real number? The bottom line answer is no. Actually, these terms will approach infinity. Okay. But really 4D, just to know that suffices to answer the question, and that better be my answer, right? 9-3. Correct. No, and my hint is what's R? R is 3/2. That's too big. That's too big. And basically, if R is a positive number greater than 1, then it's either going to shoot towards infinity or negative infinity. That's the bottom line. So basically, this sequence kind of acts similarly to this sequence here. These terms will diverge towards infinity, right? But bottom line, 4D, they do not approach a number. Now, if you have a geometric sequence, here's the bottom line. If you have a geometric sequence, and it's not a constant sequence, I guess you could say, then it'll approach 0 if R is close enough to 0. I think that was the case with 3. No, with 5. With 5, R is close enough to 0 so that the answer to 5B is 0, actually. Yeah. So the terms of a geometric sequence approaches 0 if and only if the absolute value of R is less than 1. Now, I will say this. Oh, you're welcome. A few comments. If R equals 1, then you have a constant sequence. So that does approach a number. Okay, it does approach a number, right? So for example, 7, 7, 7, 7, and so forth, that approaches 7, all right? But if R is greater than 1, I'll tell you right now, that's messed up. In fact, in general, if the absolute value of R is greater than 1, then the terms will not approach a real number. It's too messed up. Okay, the goal of this is to get you thinking about geometric terms and what they do. All right. But really for 4D, no. But it's good to know why. All right. It's not so much a matter of memorizing rules. It's a matter of kind of knowing how to play with these things. Okay, seeing what you're observing. These are not much better than these. These guys approach infinity. These guys approach infinity slower, but basically you have the same thing happening. R is too big. It's bigger than 1. All right. Okay. So I think we're ready to go back to the induction one now. Let's see. So here's an idea. Okay, let me just kind of. Okay, so here's an idea. What if I play the Khan Academy video on induction and keep the chat on and pause? So how about we do this? I can play the Khan Academy video, and if you want me to pause, or if you have a question for me in the chat, we could do that. Does that sound reasonable? Because maybe Salman Khan may have a clearer explanation. We could start for a minute. If you think it's bogus, let me know. Let me know if it's bogus. But some people benefit from this video. Okay, the Khan Academy videos are often helpful. And they've gotten better with time. They haven't always been good. Okay, so I'm going to go to my website. And I do showcase the video. It's right on my front page, I think. Oh no, this is my stats one. Okay, 141. No, I got more efficient. Okay, so it's under the final material. Whoops. No, it is here. Yeah, the Khan Academy video on induction. So yeah, this is part of the class notes for the final. Well, what would have been the final exam, right? The last 4 chapters. Okay, and I've showcased it here, right? Khan Academy on induction. Maybe later. Yeah, donate if you feel like. If you like the video, you can donate to Salman Khan. All right. Okay, so I'm still in chat. Oh, hold on. Let me restart this and unmute it. There we go.
The sum of all. I'm going to define a function s
Oh,
of.
by the way, I really should do this. I should pause the recording. Sorry. I can record again. All right. So I just showed the Khan Academy video and induction, which could be helpful. And I was just mentioning that on 17, some of these are arithmetic, and G, for example, is geometric, but not all of these. Well, some of these are neither arithmetic nor geometric. And in any case, for 9.1, I did not presume knowledge of 9.2 or 9.3. So I wanted people to develop patterns kind of independently to kind of motivate what we do in 9.2 and 9.3. So 17, you were really thrown out into the woods and kind of, I was kind of forcing you to make fire out in the woods, seeing what you come up with. All right, so let's take a look at let's look at 17F to look at some structure. So this might help orient students in case you're feeling kind of lost. Okay. So building things from scratch. Okay, 17F is a good example of having to build something from scratch because 17F is this is 9.1. This is neither arithmetic nor geometric. So even after 9.2 and 9.3, those formulas won't help you in the later sections. You got to build this one from scratch. Okay, although the pieces are all in 9.1. All right, so I'll keep this in, well, let's see. I'll do this in magenta, kind of this magenta color. All right, 9.1, 17F. Okay, this one over here. All right. Okay. All right, so let's go to magenta. Okay, so the first section of chapter 9 is 9.1. When we were introducing sequences and series, I wanted people to kind of play with functions of n. 9.1, 17F. All right, so when you look at these signed fractions over here, right, you could say that each of these terms, each of these fractions has three pieces, right? You have the sign, whether it's positive or negative. You have the top, the numerator, and at the bottom, the denominator. Now, I know that if you're dealing with something like, 1/2, 1/4, 1/8, you might just want to think of that as a straight geometric, right? And that's just basically 1/2 to the n, basically, right? But here, it might be helpful to actually decompose these into pieces, right? So the sine alternator piece, you can see this is an alternating sequence, right? It's an alternating sequence, positive, negative, positive, negative, positive, and so forth, right? So it's an alternating sequence. All right, so in fact, I'm going to do that piece in blue. All right, let's do this piece in blue. We want a sine alternator. All right, what is the sine alternator that we want? Let's start with that. Okay, now a sine alternator will often look like this. So we have a sub n equals, oops. So my final answer will be in this box, basically. All right, we're going to need a sine alternator. All right, so -1 all to the what? A sine alternator normally takes on that kind of form. -1 all to something. All right. Now, what if we start with -1 all to the n? That's a good first guess. It turns out that will work because remember, in our pre-calculus class, we're assuming that we're starting with n equals 1 in pre-calculus. I know in calculus, you often start with 0, but in our pre-calculus class, we often start with 1. All right, 1, 2, 3, 4, and so forth, the positive integers. And then what is -1 all to the n? Basically, well, -1 all to the first is -1. That corresponds to a negative term. Oh, so it's not, oh, actually, no, it's not going to work. I just realized it's not going to work. Yeah, because we're starting with n equals 1. All right. So if we start with n equals 1, we start with -1. That is a negative sign term, right? -1 all squared would be positive. All right. -1 all cubed would be like a negative. -1 all to the fourth would be a positive. All right. So this sine alternator is a bit off Okay, this sign alternator, if you're starting with n equals 1, like in our pre-calc class, it does start negative, then positive, then negative, then positive. Now, the problem with this sequence is that it's the other way, right? This sequence starts with, I'll put it in red. This sequence starts with a positive, then it goes negative, positive, negative. So what do we do to this sign alternator to get this sign alternator? Well, -1 all to the n times, how do you flip the sign? You multiply by -1, or more precisely, -1 all to the first. When you multiply powers of -1, in this case, what do you do to the exponents? You add the exponents. So we have -1 all to the n plus 1. And this sign alternator, actually you do need n, something like n plus 1 up there. That sign alternator will get you positive, negative, and so forth. All right. So in our pre-calc classes, we're starting with n equals 1. Okay. Then we do start with -1 all to the n plus 1. When n is odd, this has to be even. And then we get a positive sign, right? Like a positive 1 as our sign. Now, bear in mind that there are other sign alternators that'll work. Basically, when n is odd, this has to be even. So what else would work? We could also use, for example, I'll put these in purple. What else would work? -1 all to the n minus 1, or n minus 3, or n minus 5. Basically, any expression in the exponent that's guaranteed to switch the parity from odd to even and vice versa. All right. So this will work as a sign alternator. You could have n minus 1 for that matter. All right. That's with a sign alternator. Okay, times, I'll put a little dot here. All right. So what will work for the top and then the bottom? All right. Okay, so for the top, let's see here. 2, 4, 6, 8, 10. Sounds like Art Benjamin, right? 2, 8, 2, 4, 6, 8. Who do we appreciate? Okay, let's bring up another board here. And I mentioned this before when I mentioned parity in the notes. All right. Okay, so for the top, let's see, what color would work for the top? Okay, let's try green. Let's try green. Okay, so what's going to work for the top? All right. So once again, and we start with 1, 2, 3, 4, and so forth. What are the tops doing? The tops are going 2, 4, 6, 8, 10. 2, 4, 6, 8, and so forth. What do we do to 10? What do we do to n? What do we do to n in order to get these? What do we do to 1, 2, 3, and 4 to get 2, 4, 6, and 8? It looks like we're doubling them. 2n. Whoops. 2n. So when n is 1, 2n is 2. When n is 2, 2n is 4. When n is 3, 2n is 6. When n is 4, 2n is 8. All right. So it looks like 2n will be good for the top. All right. Now for the bottom, I have all these colors here. Looks like a big Pink Floyd poster. How about turquoise? All right. For the bottom, what can we use for the bottom here? All right. Now the bottoms are going 3, 5, 7, 9, 11. I'm going to build up on this. 3, 5, 7, 9, and so forth. What do we do to these middle values to get the bottom values? What do you do to these 2n values to get these values? It looks like 2 to 3, 4 to 5, 6 to 7, 8 to 9. Looks like we're adding 1. So methinks that 2n plus 1 will be a good function of n for this third row over here. All right, so this should work. And I would accept answer only, but of course, as a student, you want to learn from this thought process, because otherwise, if you don't learn these fundamentals in 9.1, then you're going to be very lost when you get to this stuff in Calculus 2. A lot of STEM students say that Calc 2, Math 151, is the hardest class they take. Period. The hardest class they take. The hardest calculus class, the hardest STEM class, the hardest class. So it's good to know why these things work. Okay, I don't want to discourage you. I'm just saying that you got to be prepared for this stuff. I have the answers somewhere, right? I can get it. Right. Well, I'm not hiding. You already have the answer, so I shouldn't be so discreet about it. But F over there, right? All right. So a sub n equals, again, in pre-calc, we start with n equals 1. Okay, if we start with n equals 0, then -1 all to the n would have been good if we started with n equals 0. But I had to remember that in pre-calculus, we start with n equals 1 usually. A sub n equals, and then these are the two most common sign alternators in this case, where we're starting with n equals 1, and we start with a positive term in an alternating sequence. So here's our answer, and yeah, here's mine. Okay, in the back. Okay, so a sub n equals, the sign alternator could be -1 all to the n minus 1 and plus 1, right? N plus 3 and minus 3 and so forth. The top 2n. Okay, basically there's not too much flexibility with these other pieces. We're starting with n equals 1. There's not much flexibility here. The top 2n, the bottom 2n plus 1. If a student had another variation, I'd be very questioning about that. So yeah, the top and the bottom, there's not much variation. The sign alternator, there are various ways to write it down, but basically almost all students would either pick this one or that one. I don't know why you do -1 all to the n minus 3, unless there's some sort of long-term plan, unless you have some sort of weird Calc 2 problem. All right, so building blocks. Okay, because this is not geometric, right? You got to tear it down into building blocks. G, however, you can either do that breaking apart into building blocks, do both, do that, and then remember, hey, wait a minute, this is a geometric sequence. How can I use that formula? Also, there's a question, how do you simplify some of these geometric expressions, some of these formulas? Yeah, well, some of them are kind of hard, right? 9.3. Yeah, you mean like these things, right? Like 4a, that thing there, right? And yeah, these things are kind of tricky. So you meant something like this, right? So yeah, this kind of a simplification would be kind of tricky. Let me go back to the chat. Oh, 11a? Right, that was similar, right. Okay, although this one, this was pretty much basically sign hacking. So basically you may have ended up with this. If you go through the formula from 9.3, you may have ended up with this. But some math professors might go, well, yeah, but that looks a bit sloppier than you need it to be. Like that negative sign, we try to minimize the use of that negative sign. So why don't we go ahead and multiply in one copy of -1? And when you do that, by a similar reasoning as what we did over here, right? It's basically the same reasoning as what I did over here, right? When you multiply powers of -1, you add the exponents, right? So here it's basically -1 all to the first times 3, right? But the 3 just stays there. -1 all to the first times -1 all to the n minus 1 is -1 all to the n. And this is a slightly nicer version of that. Now, on a final exam, I would have accepted either form on my 141 final, but by the time you get to Calc 2, you should be aware of this kind of algebraic hacking these kinds of gymnastics. All right. And then up here on 4A, yeah, this required a fair bit of gymnastics. Yeah, because for example, to get from here to here, it helps to recognize that 9 is 3 squared. When you divide powers of 3, you subtract exponents. Okay, so getting from here to here, a Calc 2 student would be expected to understand how we can get from here to here, but it may take time for you to kind of see it. But as a preview of Calc 2, I do encourage you to think about these rules of exponents, right? Remember the laws of exponents from chapter 0, which was the hardest chapter of the class, remember, right? Okay, and see if you can get from here to here. That's a good exercise. All right. Were there any further? Wow, it's a 10:32. I'm still up. I guess my tea's still working. I'm still up. You're to be credited for your perseverance. I'll post this video up, right?
Thank you so much, Professor.
Oh, thank you. Yes, and because I'm sure that many students have similar questions. You know what? I'm sure the class thanks you. Yeah, the class will find these very helpful. Thank you. And
Have a good night. Bye-bye.
Bye. Yes. Thank you. Yes. Are there any other questions? I know it's 10:32. I appreciate your hard work. Any other questions? See, any other questions? I'll wait a minute, and then if there are no other questions, I'll sign off. Any other questions? Okay.